Hello and welcome to the AVS e-talk on soft electronic and microfluidic systems for the skin. Today's presenter is John Rogers. He's a professor at the Materials Science and Engineering, Biomedical Engineering and Medicine at Northwestern University. We're going to have a 1-hour presentation today from him. And I wanted to give you a few reminders before we introduce John. When you logged in, you are automatically muted. You can turn up your volume, make sure your screen is in full view to review this presentation. This is a 1-hour presentation with no breaks. If you'd like to ask a question, please type them in the Q&A option at the bottom of your screen. This is the place where John will be able to review the questions in one location. If you have any technical issues, please use the chat feature. Thank you. Just a couple of disclaimers and copyright notices. This presentation is based on sources believed to be reliable. And the authors and instructors and presenters do not endorse any products, processes, manufacturers, or suppliers. And nothing in this e-talk should be interpreted as implying such an endorsement. And any material contained in this e-talk was copied with the permission of the author and instructors of the notes. To obtain releases from other materials, since we do not own the copyright of this material in this e-talk, any permission to use this material must be obtained from John. A couple of upcoming events. We have a Mid-Atlantic Chapter AVS short course program on the semiconductor device manufacturing and overview. This course is a virtual program. You can register online under the AVS website education tab. We also have some upcoming e-talks and webinars this fall. The next one is in November on what limits solar cell efficiencies, so please check that out, in addition to a couple more coming up in December. You can also register for these on the AVS website under the Education tab. And a few technical meetings. At the end of this month, we have our AVS 67 Virtual Symposium. This is a broad range of topics covered in 4 days online. We have awards, plenaries, inviteds, student talks. I invite you to check that out. It's coming up at the end of the month. Registration is open. In addition, we have some spring technical meetings that we hope to be in person: FCMN 2022, SD 2022, and ICMCTF 2022. These are all taking place in California, and details can be found on the AVS events calendar for each meeting. And if you're not currently a member, it's always a good time to join. Membership gives you access to publications, professional career development, technical resources, and discounts on registration to symposiums, meetings and exhibits, and short courses and webinars, and more. Check it out on the avs.org website. And finally, remember to complete the online evaluation form for today's AVS e-talk on soft electronic and microfluidic systems for the skin. I'd like to introduce your presenter, John Rogers. John, thank you for joining us today and preparing this e-talk. And I'll invite you to share your screen.
Great, thank you, Heather. So I'm going to go ahead and share my screen then and kind of get started. So appreciate this opportunity to kind of share some of the research that we've been doing in my group with this particular community. And I focused in on activities in the development of soft electronic and microfluidic systems designed to integrate and bond to the surface of the skin is kind of the focus. And I'll start with the background and motivation and then step you through the electronic and microfluidic technologies that represent kind of the highest state of maturity for these types of platforms. It's going to be pretty much an overview of different types of devices and capabilities, but I'd like to emphasize there are tremendous research opportunities in this space. And I think the growing awareness around remote patient monitoring, intersects with, this stream of research, in a very powerful way, especially in the context of, how people are viewing healthcare, delivering the future in the context of, the pandemic and some of the, capabilities that have come to light, in that broader context. So, as was mentioned, I'm here at Northwestern University. My core expertise is in material science and engineering, but much of what we do is highly interdisciplinary. We're really focused on system-level capabilities that arise from new insights in materials. So not strictly materials, but we do a bit of electrical engineering and chemistry, biomedical engineering, mechanical engineering, and so on. Where the interface to the clinical community is very important for us. So I have an appointment in our School of medicine. And as you'll see, a lot of these technologies have medical uses where we're sort of deep into, pilot scale studies with human subjects across a range of patient populations and conditions. So that's kind of an overview. And as I mentioned, I'll probably go pretty quickly. So hopefully I'll, have enough time, for questions and discussion toward the end of this 1 hour slot. And if anything's unclear, then you can feel free to kind of dig in, and I can kind of respond and clarify various items as necessary. So the overarching view around what we're trying to accomplish here is to kind of reformulate microsystems technologies, generally speaking. So electronics, optoelectronics, photonics, MEMS, microfluidic systems to look more like biology. So away from their traditional flat planar geometries, typically set by the characteristics of the substrates, the semiconductor wafers, the glass plates, and so on. To adopt the soft mechanics and curvilinear textures and time dynamic surfaces that you see in biology, the brain, the heart, the skin, all sorts of soft tissue systems where that form of integration could be very powerful for monitoring biological processes, maybe intervening, delivering therapy in new ways, maybe doing both sensing and delivering therapy in kind of a closed loop fashion. Tremendous set of opportunities here in biocompatible microsystems technologies, where a lot of the innovations can be driven sort of at the materials level and the level of device design, but where successful outcomes could potentially have a strong impact on how we deliver healthcare in a more cost-effective manner that improves patient outcomes is kind of the idea. And so if you want to integrate with biology, it's useful to think about engineering design principles that you see in living systems. And this is really kind of a focus on skin, which will be kind of the primary topic of the presentation today, where you really see the incredible range of length scales, functional materials from sort of nanometer to meter length scales. It's multi-layer heterogeneous combinations of solid materials, liquids. It's based on ionic flows and electrical currents, and it's mechanically active and reconfigurable, all sorts of things that are very powerful, far beyond anything that's possible in man-made systems. And maybe you can sort of focus on certain elements and begin to try to reproduce those in artificial systems to facilitate this type of intimate integration that we're envisioning. Is this sort of next generation wearable going beyond sort of a blocky piece of electronics loosely coupled to the body at the wrist to skin-like devices that can be mounted at any location, anatomically relevant for a particular medical need. So that's kind of the idea, but it's not the only sort of direction one could think about in research around bio-integrated electronics, not just skin-like platforms illustrated on the left here, but in the center, we're also interested in water-soluble or like physically transient, biodegradable devices that can perform a relevant function, but for a finite time period matched to an intrinsic biological process. There's a lot of sort of interest in that space. It represents a major area of activity for us. And then kind of in a more speculative direction, you could also imagine attempts to create three-dimensionality in electronics or optoelectronics to sort of mimic the kind of 3D open network architectures that are kind of ubiquitous in biology. So a number of different kind of interesting research opportunities. I'll focus on this first one where we're attempting to establish the foundations of thin skin-like electronics that can, of course, integrate with the skin, but also surfaces of internal organs as well, the heart, peripheral nerves, brain, lung, diaphragm, kidney, bladder, all sorts of opportunities that we're actively exploring, and others as well. So what is the problem statement? I mean, just to reiterate, what one is attempting to do really is to reformulate this kind of technology to look like biology from the standpoint of physical properties, electrical properties, in classes of materials that are intrinsically biocompatible. And that's a fairly daunting task, thinking about, man's most sophisticated forms of electronics, how to adapt those, like the silicon integrated circuit, to enable integration with the brain. Like, how do you do that? And it really requires a radical rethinking of, the constituent materials, the design architectures, and so on. And there are kind of two streams of work in this area of, bio-integrated systems. One is to, reestablish completely new classes of materials that can replace silicon and replace copper and replace silicon dioxide and so on to serve as the building blocks for devices that could be constructed with materials that are naturally and intrinsically compatible with biology along the lines of geometry, mechanics, and chemistry. The other would be to say, what can we do to reshape, recast, deploy in novel ways conventional materials? So could you use silicon not in a wafer-based form, but maybe in the form of a nanomaterial? And could you then create hybrid integrated systems that would combine inorganic materials like silicon, gallium arsenide, indium phosphide, various types of metals with organic materials, polymers, for example, to create kind of a hybrid solution that could combine the best of both worlds, biocompatible organic materials with high performance inorganics. And that's kind of the strategy that we've taken. And, there's a lot to be said about, the foundational materials aspects of these kinds of schemes. I'm just going to skip over all of that. I mean, that's kind of a set of ideas and concepts that, we put in the literature and other groups have contributed in a very significant way as well. And just kind of skip to the end, which is to say that, if you're careful about how to structure these hard materials and to combine them in these hybrid, architectures, then you can achieve devices that have sort of state-of-the-art electronic performance, but the physical properties match to soft tissue systems of the body, like the skin. So you can really create skin-like electronics using these kinds of schemes in nanomaterials, heterogeneous materials integration, using mechanical engineering combined with electrical engineering to optimize not only kind of the circuit performance, thinking about circuit layout, but also the mechanical performance by configuring these elements in ultra thin forms and in serpentine springy like interconnects and embedding it all into a soft biocompatible elastomer like a silicone polymer. It's kind of the strategy that's worked pretty well for us. And over the years, we and like I said before, others have figured out how to put together these building block materials into functional systems that again resemble the skin, can integrate with the body like a second skin in a fashion that's physically imperceptible. So you can put these devices on, they can monitor physiological processes using that skin interface to reproduce what's done in the clinic, but continuously in a real world environment. And so we've been working on this for more than 10 years now. And so I think we have a lot of the functional elements here that you can begin to assemble to address specific clinical opportunities, unmet needs in patient care. And we kind of started down that path, but it's a set of technologies that's not only characterized by comfort in terms of how the devices integrate with the body, but in terms of measurement fidelity. So these devices really do sort of follow the natural contours of the skin, and that's important because it lowers the measurement impedance for characterizing underlying body processes. And so this is a colorized STM view of one of these very thin filamentary serpentine mesh constructs, which kind of supports all of the high modulus but high performance electronic materials resting on a replica of human skin. Can you see how it's able to geometrically conform? It turns out to be very, very important. And so with those devices, you can begin to do sort of clinical grade measurements, but outside the clinic, going far beyond what's possible with wearables as they exist commercially today. So you can measure not only heart rate and heart rate variability, but you can capture the full electrocardiogram, which is important. And physicians, cardiologists know how to interpret those waveforms to assess cardiovascular health. But you can do other things that also require an intimate interface to the skin. You can measure precision hydration level, the water content of the stratum corneum and the epidermis, very important for diagnosing various sorts of dermatological conditions. You can also embed pressure sensors. So you can measure the time dynamics of pulsatile flow through near surface arteries using these kinds of devices. So essentially arterial tonometry, which can provide insights into hemodynamics and vascular tone and even blood pressure in certain cases. So you can begin to do a lot of different things. And there's a whole constellation now of different types of devices coming out of our labs and other labs kind of around the world to address all sorts of different opportunities, I guess, in clinical care, and thinking about remote care and big data and continuous data collection as a radical departure from the kind of episodic assessments of health that are performed when a patient, and only when a patient, presents themselves to a hospital. So really kind of rethinking about how we do healthcare, and doing it without the wires, without any kind of cumbersome hardware is kind of the goal. So from a material standpoint, whatever these devices do, they have to do it in a way that's absolutely burden-free. Otherwise, people just won't use the technology. So that has to be the name of the game. The thought process is a device that goes on the body and then you forget that it's there. So physically imperceptible in that sense. But at the same time, clinical grade and clinically relevant data streams that physicians know and understand how to interpret, where there's a database of many decades of insight. So it needs to be clinical grade. It needs to be imperceptible. So we and others have developed a broad portfolio of sensors. And I think there are lots of future opportunities and new kinds of sensors now that you have kind of a framework that works. And I'll describe some specific examples that we've been pursuing. You can really begin to think about not only conventional sensors of physiological processes, but novel ones as well, where each device is providing multiple types of sensor functionality, and you can mount multiple devices across the body. So multimodal and multinodal in that sense. But the focus on clinical quality, continuous, low cost, and available to everyone. So many different things are possible. I'll just give you some specific examples now of clinical uses that we've been very interested in, really kind of pivoted our research activities, or maybe expanded them would be the way to think about it, to continue basic research on the underlying materials and the technology, but also think about deployment and custom design to treat specific patient conditions. We started that probably 6-7 years ago. And our first effort was in neonatal intensive care. And we figured that, maybe this is the class of patient that could benefit most strongly from these kinds of wireless skin-like devices to eliminate the kinds of tapes, adhesive tapes and hardwired connections that are currently used to monitor vital signs in the neonatal intensive care unit. And so this is a slide, sort of an ancient slide at this point, maybe 6-7 years old, but it was just a Photoshop rendering of what I hoped we would be able to do with these ideas. And we actually were successful in making that happen. So it's quite a heavy lift, but you put all these concepts together, you can now with 2 devices, battery-free and wireless in their operation, reproduce all the vital signs monitoring that's done in even the most sophisticated neonatal intensive care units, like the level 4 facility that we have here at Lurie Children's Hospital in downtown Chicago. So one of these devices goes on the chest. That's what you're seeing here on a 32-week old baby. So this is a premature baby. And we've deployed these devices, about 250 neonates, as a way to establish the accuracy. So we're monitoring all these vital signs with these skin-like devices at the same time the babies are being monitored with the traditional wired hardware. So we have one-to-one comparison, to clinical gold standards. And it turns out that these work quite well. Here, we've expanded our deployment into the pediatric intensive care unit, slightly larger babies, but still needing, in many cases, full 24/7 vital signs monitoring. Getting rid of the wires allows parents to engage more naturally and more frequently with their child, and that turns out to be very important for the healthy development of the child. You can see the device on the chest. That's measuring electrocardiograms, so we can get heart rate variability, respiration rate. There's a clinical grade temperature sensor also embedded, pretty close to core body temperature when the babies are in the isolette from that reading. And then the device on the foot, you can see down there, is measuring blood oxygenation, and so that really rounds out the full complement of vital signs that are measured, in a NICU facility, in a well-equipped hospital today. This is just a kind of an interesting picture to sort of illustrate the mechanics of those devices. As I mentioned, they're engineered specifically through these hybrid hard, soft, deterministic composite material structures, the way you can kind of think about them, to mimic the properties of the skin. So thicknesses, thermal mass values, mechanical moduli that are very, very similar to the epidermis itself. And so it moves in a very natural way with the skin. And it avoids the kind of interface stresses that can be harmful to the skin and can cause delamination. So you can get these devices to stick with even just a very mild adhesive, and that turns out to be very important as well. So these are the kinds of things that are possible. We published that paper in spring 2019. We were shortly thereafter contacted by program managers at the Bill and Melinda Gates Foundation and by their partners at the Save the Children organization to think about taking those technologies and deploying them in lower and middle income countries where there's really no monitoring capability at all. So not just kind of getting rid of the wires, but introducing, the monitoring capabilities themselves. And so that was an exciting opportunity for us. We engaged and we're able to adapt the devices I just described to you, kind of ruggedize them, allow them to operate without access to wall plug power for deployment into various countries in Africa. And so we're in Zambia, Ghana, Kenya, India, and Pakistan currently. And we've done many thousands of devices at this point, and should hit 10,000 by the end of the calendar year, in spite of all the difficulties associated with COVID-19. And so those modified platforms are described in a paper in Nature Medicine that we published last spring. If you want to see the details there. But these are clinical grade. These are kind of the vital signs that are captured with those devices. You can see the raw data traces at the top there. Those are ECG waveforms, two-color photoplethysmography. We're also, in this case, capturing heart sounds. So seismocardiograms also measure chest wall movements, so you can get respiration directly from the mechanical motions of the chest. And then you take those data streams, you apply data analytics routines with them to extract these various vital signs: heart rate, SpO2, respiration rate, temperature. And because we have two devices running in a time synchronized way, you can also get differences in temperature between the chest and a peripheral location like the foot or the hand, and that can tell you something about circulatory behavior of the infant. So these are the kinds of things we're doing. We're deployed in 5 continents, 23 countries at this point, through a startup that we had to put in place to execute on the Gates program. But that startup company, Cybal Health, has partnerships with a number of large companies in medical monitoring technology, Draeger, and in medical insurance, Anthem, as well as funding from the NIH and BARDA. So these are the kinds of things you can do. And once you get your foot in the door and you've established an ability to do what's done conventionally in a NICU, then you can think about going beyond. As I was mentioning before, now you have these platforms. What other kinds of sensors can you add to the mix that might be interesting, going beyond NICUs of today to NICUs of the future is kind of the idea. So at the chest unit in this latest deployment, we have a wide bandwidth accelerometer, so we get body orientation, so we can determine sort of restlessness, activity levels of the baby. We can track when the baby's engaged in kangaroo mother care, which is a kind of care that's being encouraged in regions of the globe where isolates are not available. So this is engagement with the mother. You can sort of track that and time that just by looking at the orientation of the baby by analyzing data from that chest unit accelerometer. But it also has high bandwidth response, so you can determine cry time, cry tonality. But it's not a microphone, so you're immune to ambient noises. You're basically measuring subtle vibratory signatures of crying from motions of the chest. And so this represents a new set of parameters that you might consider, in improving the care of patients of this type. So these are some ideas. The other thing you can do is, because the chest unit and the limb unit are time synchronized, you can determine hemodynamics. That is, you can determine how quickly blood flows through the vasculature of the body, and that pulse wave velocity is derived from the pulse arrival time, the difference in timing between when a pulse of blood is initiated by a cardiac cycle and when it arrives at the foot or the hand, for example, can be correlated to systolic and diastolic blood pressure. That's kind of known in adult patients, but the ability to do that in infants is particularly profound, because use of arterial lines is very, very difficult due to the small, fragile nature of the arteries, and you can't use a cuff for a blood pressure measurement very often, because you'll bruise the tissues. So being able to do non-invasive pulse-to-pulse measurements of blood pressure turned out to be very, very powerful. So we just published a paper illustrating feasibility of that kind of thing in pediatric population. But anyway, just thinking about what else is possible, what could be measured that's not measured today, enabled by these kind of soft electronic platforms is kind of an interesting set of opportunities, and I'm sure there are a lot of great ideas out there in the broader community. We're only pursuing a small fraction of the possibilities. So I think this is a rich area for research with a direct potential for impact on well-being of populations. So we have a number of other devices that I would say are kind of entering the translational pipeline. We just got FDA approval on the devices I described in the last few slides, but a number of others are kind of in in that pipeline, moving out of the academic lab into the real world. I won't go through the details here, but just give you a sense that there are a number. I'll give you a couple of examples, say a few more words. So we're interested in neonatal pediatric health, but also maternal fetal. So right before the neonate, how's the mother doing? How's the fetus doing? Can you monitor their health during delivery, for example? Can you use the same ideas in wireless soft electronics to make those tasks in monitoring a lot more readily available at a global sense, and a lot more patient-friendly without the wires. And so we have 3 units now. They're all wirelessly synced together. One is capturing maternal vital signs, a pair of devices for that. And then we have a device at the base there that uses Doppler techniques to measure fetal heart rate, and it also has EMG sensing capability to capture uterine contractions. So everything is being captured continuously and in a wirelessly synchronized way. And I won't go through the details here, but everything sort of aligns with clinical standards. So we can measure ECG. We can see fetal contributions to the ECG. We can measure heart sounds. We can see fetal heart sounds. We can capture fetal heart rate. And we can measure uterine contractions in a way that correlates to gold standard. In some ways, it's better. The signal quality is better than what we see even at Princess Women's Hospital here in Chicago. It's the gold standard shown there. But we've taken advantage of our engagement with Gates and Save the Children to deploy these devices on pregnant women during delivery in Zambia primarily. So almost 500 women have been monitored. And so this is big data. We have continuous heart rate, respiration rate, systolic blood pressure, SpO2 from all of these women. And I think the future here is to develop deep data insights into how childbirth happens, and what are the trajectories that different women enter upon. Can you predict when the baby's going to be delivered? Can you predict whether there are going to be health risks associated with the delivery to the mother or the newborn baby? So there's a lot of opportunities in machine learning, artificial intelligence built around these devices and the data streams that they're producing, and we will be announcing new programs along those lines in the very near future. So that's what we're doing in maternal and fetal health. Let me say a couple of words about opportunities at the other end of the age spectrum. So older adults, elderly populations. There we've been interested in stroke survivors specifically, and in working with rehabilitation specialists at the Shirley Ryan Ability Labs, a very large rehabilitation clinic here in Chicago. And one of the problems that stroke survivors face in many cases is that they have to relearn how to speak. They have to relearn how to swallow. So they suffer from aphasia and dysphagia. And they come into the clinic and they go through various exercises, rehabilitation protocols. In a lot of cases, they improve while they're in the clinic, and you can kind of see that. But then they return home and a lot of those improvements die away. And so we were approached by clinicians associated with the Ability Lab to develop a technology that allowed them to track continuously patterns of speech and swallowing events during the course of a normal day outside of the clinic. And so we are able to take these soft hybrid electronic systems, configure them to mount on a special part of the anatomy. As I mentioned before, you can really place these devices anywhere. You don't have to be restricted to the wrist, obviously. And it basically sits at a soft tissue location at the base of the neck called the suprasternal notch. And it records motions, subtle motions, gross motions of the body, everything in between, with a high bandwidth pair of accelerometers, a single accelerometer or a pair. There are different things you can do with differential detection. So this was published in February of 2020, and we were kind of deep in the process of exploring what these devices can do and how you can sort of process the data to extract things like speech. Again, it's not a microphone, so you're immune to ambient sounds and a lot of the privacy concerns that would otherwise be associated with continuous microphone-based recordings of speech kind of go away. It's a big advantage of these systems. If you get to swallowing, you're close enough to the carotid artery, you can actually capture motions associated with pulsatile blood flow through the carotid, so you get heart rate variability, respiration rate, you're coupled to the chest wall cavity, respiratory sounds, coughing, wheezing, that kind of thing. There's a lot of information that you can capture with a very simple device located at that part of the body: sleep dynamics, motion, steps, orientation. And it's really the soft nature of the electronics that allow this to happen, because that part of the body is relatively sensitive. You can imagine, difficulties in, strapping an Apple Watch to your throat, it's probably not going to work, or a Fitbit. But, with these soft Band-Aid type devices, it's no problem at all. They go on and you forget that they're there over time. But this is what the data actually look like. So you're getting X, Y, and Z accelerometry. And you can see in the upper traces there, you can see signatures of respiration. These little blips, that's heart sounds. And so you can pull those out. You can see swallowing events over here. And each of these activities has kind of a unique temporal and spectral signature associated with them. And you can use digital filtering and artificial intelligence algorithms to really identify uniquely these different types of events, and you can count them up and you can track them and you can measure their intensity and so on. And so it turns out to be very, very rich, very simple device, but you can capture a tremendous amount of information. So we're deep into that. This is February, March 2020, then the pandemic hits, and we begin to get a lot of requests for this device from the medical community downtown who are aware of our work in this space. And their idea was that we could use this uniquely to track the key symptoms associated with COVID, which happen to be fever, cough, and shortness of breath. Kinds of things that you can't measure from the wrist. COVID's a respiratory disease. You don't want your wearable device to track COVID to be sitting on your wrist. You want it on the chest, and in particular the suprasternal notch. So we got pulled into this pretty aggressively. We were designated as essential personnel. The whole group kind of continued without pause. I don't think I missed a day through the whole period. And we had to sort of re-engineer some aspects of the device, make it burden-free in terms of how the data is captured and translated. And I won't go into details here, but it's very simple. You take the device, you put it on the suprasternal notch. It's a dual-sided bandage adhesive. It keeps them there up to 36 hours. You take the device off, you put it on a wireless charging pad, recharge the battery, and when that happens, it automatically initiates a data transfer process that moves the data from onboard memory in the device to a local iPad, and then from the iPad to a HIPAA-compliant AWS cloud server. So we're about 60 weeks into this, 550 subjects, about 100,000 hours of data, about 5 terabytes worth. And the whole thing terminates in a graphical user interface, allows physicians to look at what's going on with their patients in terms of these key symptoms, not just with the patients who are in the hospital, but also those who have been released to the home. In a lot of cases, they're also using these devices to monitor their nursing staff, for example, frontline health workers, to maybe pick up early signs of symptoms to inform how they're managing their staff. So that's kind of what it looks like. We published some fraction of those results in PNAS just a few months ago, and here we're focused not on vital signs, but like going beyond. So counting coughs and measuring cough sounds and cough intensity. It's sort of interesting. Even in the most sophisticated ICUs that exist in the U.S., they don't do anything with cough. They're not trying to track cough. It's hard to do that because you can't do it with a microphone. You're in a noisy environment. But with these devices, you can quantitate cough. Now you can think about cough maybe as a key metric for guiding patient care is kind of the idea. So we're sort of tracking cough in all these COVID patients, again, both in the clinic, back at home, and watching how cough dynamics dissipates as they recover and different things of that sort. Cough is also interesting because it correlates to total aerosol production. So without measuring the aerosols directly, we can measure cough frequency, cough intensity, and at least determine at a semi-quantitative level how much aerosol a particular patient is generating, and that determines to some extent their level of infectiousness. And so that kind of information also kind of going beyond what's done as a standard of care, even in a sophisticated hospital, thinking about new sensor modalities, new metrics, new insights into patient status, and understanding how infectious a patient is may sort of guide how they're cared for, in a hospital setting. So this is interesting. The other thing you can think about, and this represents ongoing work, is whether you could use the device to diagnose whether someone has COVID or not just from direct symptoms, but thinking about time-dependent variations in vital signs. So one of the effects of COVID is that you're unable to respirate effectively. And so what that means is that you fatigue very easily. And what could you capture that would measure fatigability? And one thing you can do is you can ask the patients to walk around the room for some amount of time and use these devices to measure heart rate and respiration rate before and after that mild activity. And that's what's shown here. The gait is happening in the middle, and you can see that because you can count the steps. You know what the step features are in the data, and so you can look at deltas in temperature, in blood oxygenation, in respiration rate, and heart rate. It turns out to be pretty interesting, and so this is the way that we were doing it initially, and then we realized we don't even have to ask the patients to do this on their own. We can pick it up. We can determine when they're walking, and then we just look at the vital signs before and after that period. We don't have to have them follow a protocol. Just naturally move around the house, and we'll determine the level of fatigability by looking at change in these parameters, and then applying principal component analysis to make a determination based on those changes whether a patient is sick or not. So it's not necessarily COVID specific. They could have other diseases, but you're picking things up using digital data streams that have no consumables. And so maybe as a complement to more conventional molecular-based assays, or maybe you use this as a screen to determine who gets, a PCR test, for example. So anyway, different things that you can think about with advanced soft electronics, wearables, and so on. So for the last 10 minutes, I'm going to shift gears and talk about a different platform, microfluidics. Same type of concept. Can you create soft microfluidic devices that interface with the skin in a conceptually similar way to soft electronics? And it turns out you can do all of that. And again, I don't have time to get into all of the details. You can find those, in our published papers. Everything's in the open literature. But you can use soft elastomers to create classes of microfluidic devices that can just be adhered to the surface of the skin. And why is that interesting? Well, if you're thinking about assessing health, you'd like to be able to do that through biophysical measurements. This is what I've talked to you about up to this point. But the body's a biochemical system, so you'd like to be able to get access to biofluids so you can measure enzymes and metabolites and electrolytes and essential nutrients and things of that sort. And we thought about blood, then it requires, penetrating the skin, interstitial fluid, same thing. There's some risks and infection problems there. And then you can think about saliva or tears, but then sweat seemed to be most interesting to us. And there are a number of other groups that have done some nice work in sweat. And thinking about sweat, not just in the context of sweat chemistry, but sweat microfluidics. So measuring sweat dynamics, so sweat loss, sweat rate, in addition to sweat chemistry. And you can do all of that using microfluidic approaches, really sort of bootstrapping on all of the wonderful advances that the lab on a chip community has made over the last 20, 30 years, but adapting those ideas to these skin interface platforms. You can see an exploded view illustration here. We have sealed microfluidic network of channels and valves and reservoirs adhered to the skin. We have openings in that adhesive layer, so eccrine sweat moving from the surface to the surface of the skin can enter inlet ports in the back side of this microfluidic system. And then we use you either use color electrochemical methods to read out biomarkers, or what we prefer are colorimetric chemical reagents, because then you eliminate the need for a battery and a radio. And so you can do color readout of biomarkers in sweat in this way. And so you can do that. It's radically different than anything that's been done in the past. There are related efforts, really nice work at Caltech and Berkeley and University of Cincinnati and Seoul National and University of California, San Diego, where they're using kind of electrochemical approaches without microfluidics. And so that's kind of the distinction. We like microfluidics and colorimetrics, but there are these other very powerful approaches based on sort of hydrogel interfaces and electrochemical detection, and we just as reference. But this is what one of the initial devices look like. We have sort of a serpentine channel runs around the perimeter. It connects to a central inlet port. And that's designed to measure total sweat loss. And through two time sequential measurements of filling of that channel, you can measure sweat rate. And we have a color changing chemistry here. It's a cobalt chloride and a hydrogel that changes from purple to red upon contact with water. So you just look for the position of the color change front in terms of the filling, the cross-sectional dimensions, the contour lengths. You determine the amount of sweat that's been lost at the location of the skin that aligns with that central inlet port. And then in this device, we have 4 other inlet ports that connect separately to 4 circular reservoirs that support assays for lactate, chloride, glucose, and pH. So that's the way it works. Simple device, no active components. You get 4 biomarkers. You get sweat rate. You get sweat loss. It's pretty multifunctional, but simple and low cost. So you can do this. Mechanics is very important, as it was for electronics, maybe even more so for microfluidics, because the devices have to stay adhered in the presence of vigorous sweating and physical motions. And so you really need to pay attention to it. Mechanics of materials, system level design, full 3D finite element modeling through collaborations that we have with Younggang Huang's group here at Northwestern, fully optimized from the standpoint of mechanics. Won't get into the details, but those are important features of the underlying research. This is what one of the devices looks like mounted on the outer forearm. You can see the color change front at the 7 o'clock position here for that serpentine channel. That's giving us sweat loss, sweat rate. And then the 4 circular reservoirs giving us chloride, lactate, glucose, and pH. Here's what it looks like in a time sequence of images in a simple a sweat collection device. There's just serpentine channel, colored food dye at the inlet on my forearm as I'm working out. And you can see sweat begin to fill the device. You capture a few digital images. You can determine sweat loss at any given time point. And you can plot then the cumulative sweat loss as a function of exercise duration. In this particular case, it's almost constant sweat rate, which is sort of amazing how constant it is. But anyway, I'm an elliptical here. I fill the device up completely by 6:35 after starting at 5:52. You can change the geometries of these channels to accommodate more sweat if you want. But the interesting thing here is if you look at the surrounding part of my skin adjacent to this device, you see it's basically dry. And so without this device, you lose a sense of awareness of how much sweat loss has actually occurred. And I think that's the primary value of a measurement of sweat loss. Well, one value of sweat loss and sweat rate is just an awareness so you can maintain proper hydration, especially in an arid environment, for example. This would be very important. But the other ability is now you have sweat captured. It's pristine quantities of sweat, microliter volumes, but you have these different colorimetric chemistries that allow you to read out in situ the biomarkers of interest. So I'm not going to go through the details here, but just say that there's a tremendous opportunity here for developing new colorimetric assays for species in sweat. We have probably 15 or 20 different species that we know how to sense using color changing chemistries, but there's a whole broader range of opportunities that look to be interesting directions for research. But this is a silver chloroanilate assay for chloride. So it changes color in a very vibrant manner across chloride concentrations that are relevant to sweat. So for most individuals, it's lying between 10 and 100 millimolar. And you can see that, you can read it out very precisely, color change. Enzymatic approaches are also possible. So you can do glucose, for example. You have a strong color change, again, for concentrations relevant to sweat. You can do lactate with lactate oxidase, another species that you can do. pH is very easy, all kinds of different pH indicators that you can use. Low pH, extremely low pH can sometimes be an indication of dehydration, so it's relevant there. And you can also do nutritional assessments. There's an area of recent interest for us and some other groups that are pursuing electrochemical sensing schemes. So you can do colorimetric detection of vitamin C in sweat, for example. You can get calcium concentrations in sweat. You can do zinc, you can do iron. All these different species are possible. And in some cases, you can combine all these assays into one. So I showed you with 4 different assays. Here's 4, but with an additional feature that we use capillary bursting valve integration to get some sense of time dependence of the concentrations of these biomarkers as you're sweating. So early sweat may have a different collection of biomarker concentrations than late sweat, and that might tell you something about how your body's chemistry is changing during a workout. So you can do that as well. And this is kind of the way that one of these devices fills. So we have a serpentine channel over here on the left for sweat rate, sweat loss, and then we have these capillary bursting valves that are separating these circular reservoirs in such a way that they fill in a time sequential manner, one after the other, without any mixing. And so by including redundancy in these assays, you can determine, let's say, chloride concentration at 4 different time points. Glucose, lactate, vitamin C, you can do all of these things without any electronic timer. And so this turns out to be a very simple but very effective way to get time-dependent information around sweat composition. So these are the things that you can do. Now, you may ask, who cares about sweat? I really care about blood. That's really telling me my body chemistry. And that's a good question. And it really boils down to the question of what species in sweat correlate nicely and rigidly to concentrations in blood. And I think that's an open set of questions. There are species that are known to correlate very nicely. Others, need to be investigated. But what we did here is we looked at vitamin C, calcium, zinc, and iron concentrations in sweat before and after taking supplements, either a patch or a pill. And then we look at the time dynamics of how the concentration changes over time. We can compare that to literature studies of these concentrations during similar experiments assessed in blood. And so you look at the maximum concentration when that happens after the supplement is taken, and then what is the characteristic decay time. You look at those two parameters, and we see a pretty nice correlation between sweat and blood according to those two key time dynamic features. So our sense is that these are probably relevant species to measure concentrations of in sweat because they tend to track blood pretty well at that level. So I'll kind of conclude with a couple of things. So one is, what is the sort of technical maturity? I showed you deployments associated with these vital signs monitoring patches with Gates and other organizations. So Gatorade approached us end of 2016 about taking our devices, were just published in December of that year, and maybe making them into a product that they could offer their customers to provide an heightened awareness, not only of sweat loss, but also of electrolyte loss. To help guide, consumption of their core product, how to rehydrate in a more quantitative, scientific manner. And that turned out to be kind of interesting. So we did engage with them. We had to put together a small company to respond to that opportunity. We did that Epicor Biosystems. And so all that worked out. It's basically the technology I just described to you, measuring chloride, and we're measuring sweat loss, sweat rate. And so this has been featured on many different celebrity athletes, and it's about 500,000 units have been deployed this calendar year into Dick's Sporting Goods. If you want to go check it out, you can do that. You can also order these devices off of the Gatorade website. That's Serena Williams. This is what it looks like. So these are scientifically proven devices. It's not a consumer toy. It's a real precision piece of science, essentially, embodied in a cost-effective single-use patch is the way it is. And it goes with an app, allows you to capture an image of the device. It does all the color extraction. It determines the fluid fill front. You can determine sweat rate, sweat loss, and chloride electrolyte loss as well. And it correlates very nicely to clinical standards, HPLC, absorbent pads, and so on. And all this has been scientifically and rigorously studied. It's all in the open literature if you want to check out the papers. One kind of an amusing side note, and we didn't really know this was going to happen, but Gatorade decided to launch the product as a virtual product within the NBA 2K21 game. So I don't know if there are any gamers on the line, but you can go in and you can buy these sweat patches for your avatar. Unfortunately, no material science content involved whatsoever. So anyway, we're kind of cut out of that process. But anyway, it's kind of an amusing thing to see a virtual product based on your research. But ultimately, I think we're most interested in medical applications. So what is sweat good for medically today? And the one thing that we know of for sure is that it's used as a screen for cystic fibrosis. You basically collect samples of sweat, infants typically. You measure the chloride concentration. It's very high. It indicates that the baby may be susceptible to may have cystic fibrosis. That collection is happening today with kind of a hockey puck. It's a rigid platform. It straps tightly to the arm of the infant. They stimulate sweat. They collect sweat into a coiled up tube. They pull the tube out. They extract the sweat. They put it in an analytical instrument, determine chloride. And so when we were publishing our papers, we got contacted by pediatric department here at Lurie Children's asking whether we could use our soft microfluidic devices as an alternative to this approach for screening for cystic fibrosis. Turned out to be super easy. So we just have a soft sticker, put it gently on the surface of the skin. We have the chloride assay built in. We don't have to extract the sweat. We can analyze chloride in very, very tiny volumes of sweat because we're doing it within the device. And we don't have any failures due to leakage because we have a nice adhesive interface. And so that turned out to be a fun project and a fun collection of subjects to work with. What we found in terms of user experience is if you put any kind of graphic, this one has Lightning McQueen from the Cars movie on top of the sweat microfluidic devices. They absolutely love having their sweat tested. It's like a sticker they put on. So anyway, that's what it is. We published those results just a couple of months ago. Correlation to clinical standards, and maybe a good way to do this. And a technology allowed the assessment to be done in a home setting. So again, remote care being an important feature of a lot of these technologies. Don't necessarily need to bring the baby to the hospital. Just FedEx them one of these stickers, they put it on, and kind of do the assessment in the home. And finally, you can kind of take microfluidics, obviously kind of integrate it with electronics if you want to do that. There are certain species maybe you can do better, assessments using electrochemistry compared to colorimetric. Do both in single platform, sort of publish that. And in some cases, you want real-time streaming data, so you can include Bluetooth functionality. So here, the electronics module is reusable. The microfluidic adhesive patch is single use. And so you can do real-time tracking of sweat dynamics, sweat chemistry in that way. We think that's an interesting direction for the future as well. So I think I'm out of time. I want to open up some Q&A. If I have a bit of time left. I talked about electronics, microfluidics, both configured for the skin. We're a highly collaborative group, a number of different senior PIs in engineering science, clinical medicine, and sports, but the students are doing all the work. So I'd like to conclude my talk by acknowledging them. So thank you again for your attention. I'd be happy to answer questions if anybody has them.
Thank you very much, John. There are a couple of questions already in the Q&A if you'd like to go ahead and review those.
Okay, how do the devices run battery free? We use an NFC, magnetic inductive coupling scheme. Works well for babies in an isolate. You just put the transmission receive antenna at the base of the isolate. It's kind of the way you do it without batteries. For the Zambia deployments, we have to have battery because there's no reliable source of wall plug power to run the antenna. So they have a battery. How long can one wear a patch? About 2 weeks is as long as you can go because your skin is naturally exfoliating dead cells, and that kind of process is happening with a time scale of about 2 weeks. So even if your adhesive is robust, you're sitting now on a very unstable interface, and the device adhesion is compromised by that. How do you get data off the patch? It's all wireless, except for the microfluidic patches where it's colorimetric. So I guess wireless in a sense, but optical image-based. The other question is, do you have a challenge in fabrication processes compared to conventional silicon scheme? Well, we try to take a hybrid approach. So we try to leverage, whenever we can, established manufacturing infrastructure, because it's tremendously sophisticated, it's low cost. It's deployed at global scales for the consumer electronics gadgetry industry. So whenever we can leverage that, we do. But in some cases, you kind of have to mix and match different sorts of materials together in unusual ways that get outside of kind of the standards of what's done today. So bits and pieces you need to adapt, but you can leverage a large fraction of the manufacturing capacity that's already in place. And we think that's a very important feature. For example, the Gates program would not work unless they were convinced that the devices could be low cost. And the only way it's going to be low cost is if you're leveraging existing manufacturing capabilities. You can't build a new foundry, a new electronics, manufacturing facility. There's just no way that's going to happen in the near term. So that's kind of been our strategy.
Well, thank you very much. We still have time for a few more questions. So if anybody has their hand raised and would like to ask a question, please type it in the Q&A. I'm going to go over some closing slides, but that'll give you time to type in the questions for John before we leave. But I do want to thank you, John, for presenting an amazing e-talk for us. And I'm going to go ahead and share some slides here. And so you have joined us today for our AVS e-talk on soft electronic and microfluidic systems for the skin with John Rogers from Northwestern University. Again, thank you for joining us. Thank you, John, for preparing a very interesting e-talk for our audience. And I want to remind people that we do have some upcoming programs taking place in terms of short courses, e-talks, and webinars. for the remaining quarter of 2021. Some of these are virtual as we are still dealing with the pandemic, but we have a Mid-Atlantic chapter short course on semiconductor device manufacturing overview course in November. It's open for registration. We also have a couple of more e-talks and a webinar coming up in November and December. Please check out the AVS website under the education tab, and you'll find various events taking place. You can also go to our events calendar on the website as well. And we have our technical meetings coming up. The most current one coming up is our AVS 67 virtual symposium filled with plenary award talks, live talks on demand. Registration is open, so check it out. You can attend no matter where you're located in this the virtual symposium, so we hope you'll join us. We also have some spring programs, FCMN 2022, ASD 2022, and ICMCTF 2022. They're all taking place in California in person, hopefully. Go to our events calendar to find out more details on each of these meetings. And if you're not currently a member, again, it's a 365-day membership, and it gives you access to many things like our publications and technical resources, discounts on registrations for symposium and short courses and webinars. And you can go to the AVS website to check out more details about our society. And if you're a student, this is also a great time to find out about student chapters, career services, and how to get involved with AVS. And we'll have an online evaluation form. Once you log off, you should see that. If not, it will also be emailed to you. And at this time, it looks like we have a couple more questions for you, John, if you'd like to field those, please.
Yeah, let me see. Where can we have the recorded lecture? I guess you can probably answer that one, Heather.
Yes.
Are you thinking about moving to the interior of the body? Yeah, we have a number of programs on implants, cardiac, brain, bladder, kidney, spinal cord, and peripheral nerves mostly. So good point. A lot of the same ideas apply. The trick with inside the body is in encapsulation. You have to have incredible perfection in biofluid barriers if you have any active electronics. So that's been the great one of the greatest materials challenges. But let's see. Could you discuss a little bit more about internal organ patches? What is the state of the art now? Compatibility and toxicity questions. I guess all of our internal organ patches are designed to facilitate as research tools for animal model studies of basic questions in biology. So I would say we have the greatest traction around very tiny light sources that implant down into the depth of the brain for optogenetic studies of brain function. We have spinal and peripheral nerve interfaces also based on optogenetics. So these are genetically modified neurons that respond to light exposure. So it's a very powerful, relatively new neuroscience technique. And being able to implant cellular scale LEDs and to operate them in a battery-free wireless fashion allows you to do all kinds of animal model experiments that would be impossible with conventional fiber optic cable type of approach. So we've done a lot there. In terms of cardiac interfaces, I guess we're most excited about bioresorbable temporary pacemakers. So in most cases, patient care following a cardiac surgery involves a temporary pacemaker being installed to pace the heart as necessary during that critical risk period, covering the recovery period. And there are all kinds of disadvantages with those temporary pacemakers. There are percutaneous leads that can be cumbersome, and then surgical extraction of the leads can sometimes lead to damage of cardiac tissue. So we've been working with cardiac surgeons here. Just published a paper a few weeks ago on a bioresorbable wireless pacemaker. And so it operates wirelessly for a relevant period of time, about a week, between 1 and 2 weeks. And then it just dissolves away. So you don't have to extract it. It dissolves away like a resorbable suture, but it's a piece of electronics. So I would say that's an area that seems to be a very high interest to the clinical community. So that's kind of a focus area for us right now in terms of human use and an implantable technology. Another one we have is a wireless flow and temperature sensor for monitoring kidney rejection for our kidney transplant patients. So it's animal model studies now, but vectoring toward human use. I like over time, and it's a involved process. The regulatory hurdles for an implant are quite significant. It's the reason why we like skin-mounted devices. They're totally almost zero risk, so it doesn't take much to get approval to put them on humans, and that's a quick path to impact, we think, on human healthcare. And then the implantables are exciting too, but that's more like a 5-10 year type of time frame to get them approved. But those are some examples.
All right, are there any more questions from anybody? If not, I do want to thank you, John. It was a great presentation and a lot of good questions came from our audience today, and we had good participation. So I'd like to thank everyone. Thank you, John. And I do not see any additional questions. I did put in the chat John's contact information if you'd like to follow up on any of this information with him. And I think we'll let everybody go. And thank you, John. Thank you to our audience, and we'll see you at another eTalk, hopefully. Thank you.
Okay, bye-bye. Thanks.
Bye.
Bye.